Good afternoon. Here yet again for the level recession of CENG 3325 Structural Analysis. This will be part 1 of lecture 23 in the video series, and this is going to be the lecture for, I suppose, April 12th, 2018. So, today I want to introduce the force method for beams. And part 1 of this video is going to cover the theory of the force method, and part 2 is going to go over some long-form examples. So, force method. Let us look at the force method here. So, first of all, it's important to keep in mind what we're going to use this for. And first and foremost, it is going to be a method of analyzing statically indeterminate structures. Indeterminate structures, and you can use this for a whole variety of things. You can use this for beams, you can use this for frames, you can use this for trusses, you can use this for even things like support settlement. You can use this for all sorts of things. Indeterminate structures. Now, and again, we can use this for any number of different things. So I want to first look at the theory here. Let's explore the theory here. And it is one of the best methods for analyzing indeterminate forms. So this is really based on the theory of linear superposition. I did a video on this shortly before this. I believe that was 1 or 2 videos ago. And so if you want to know more about the theory of linear superposition, feel free to take a look at that. So this is based upon linear superposition. And if you recall, the idea of linear superposition is that you can simply sum up the deflections produced by individual forces to produce the effect of the combined series of forces, couples, moments, wherever they might be. So, and in our previous example, or in our previous video on linear superposition, we discussed this mainly in the context of simplifying the analysis of frames, or simplifying the analysis of beams. We said when you had, for example, many different loads applied to a structure or a beam, you could sum up the responses or the deflections or rotations of the individual simpler loadings to get the final, more complex combined loading. But we can also use this to find equivalent systems, or to separate out or turn a indeterminate system into a redundant system. So the basic idea here is that we will have or perhaps the big idea I might say, is that an indeterminate system is a superposition of multiple determinate systems. Is a superposition of multiple redundant systems, or sorry, multiple determinate systems. So in other words, imagine I have a beam. Imagine I have a beam that is statically indeterminate. So a beam like this. Consider a beam like this with end A and end B, with perhaps a point load somewhere along its length. This beam, as I have drawn it, is indeterminate. There would be 3 reactions on the left-hand side and 1 reaction on the right-hand side. We have a total of 4 reactions, and so that would be 4 reactions. We have only 3 equations of static equilibrium. This is indeterminate to the first degree. However, this is essentially equivalent to, well, let me show you this. Let's say I draw my reactions here. By, ax, ay, and maybe an ma here. Well, this is essentially equivalent to this. If this, what would happen if I removed this load? What would happen if I removed this support? So if I didn't have that there, I would still have that fixed support there. And under this point load P, let me show that being P, I would have I'd have a point load P here still, and I would still have some reactions. These would be different reactions depending on the system. AX, I would have some AX, some AY, and an MA. And this thing would deflect downward in some form such as this. It would deflect downward in a deflected shape, kind of like this. However, what happens if I were to apply, let's say, BY? Ignore the reaction here. Ignore the fact that this is a support. What happens if I just had a cantilevered beam without load P on it, but just load BY? With just load BY. So imagine I had a beam, the same cantilever beam, the same length, the same geometry, etc. The only difference is that support is replaced with just a point load of magnitude equal to BY. Well, what would happen? It would deflect upward like this. Ignoring, there would be no real loads on this. That we remove the loads that are actually on the structure, and say how this deflect if under a point load equivalent to the load in this roller here. And we would find that under this load P, this thing would deform down or deflect down a certain distance delta. Now, here's the interesting thing. We know that in reality, there is no deflection at joint B here, at point B here. So, again, because we know that beams can be treated as linear superpositions, this deformation as well must be delta. This deformation must be delta. Or, in other words, I could state, if I wanted to state this in more language terms, I could say that, let me put a little plus here. The deflection from a removed support from a removed support at B should be equal and opposite from the removed support at B should be equal and opposite I should say remove support load at B should be equal and opposite to the free deflection or the unrestrained deflection at B from the real loads. So in other words, if I remove this support and say, okay, this force B is no longer here, our pin support is no longer here, this beam is going to bend downward, and it's going to bend downward a certain distance delta. So if I have that hanging free there, if I want to force it back up into a horizontal direction, that kind of energy, the amount of energy, the amount of work, the amount of force required to do that is going to be equivalent of taking BY through a certain distance delta. Okay, and we will look at that more in a bit. So first I want to define a few terminologies, a few items of terminology. Again, the big idea is that we are going to be we will replace redundant supports or supports beyond supports beyond static determinacy, beyond those need for static determinacy, or just beyond those need for static determinacy. Determinacy with the loads those joints would support, or loads those supports would have through them. With the loads those supports would have through them. So we do have a few terms that we want to be aware of. The first one is redundant. Redundant support. A redundant support is one of the supports that we are removing. A support we are removing. Again, it is more a support that is not needed for static determinacy, beyond what is needed for a determinate structure. For a determinate form or determinate structure. And for beams, I'm also going to introduce a few terms that I'm going to reference. I'm going to define my primary beam. And my primary beam is going to be the beam with real loads and redundant supports removed. With real loads present and redundant supports removed. And my secondary beam, or sometimes secondary beams, if you have more than one, if you have a degree of determinacy more than one, you'll actually have more than one secondary beam. This is the beam with real loads removed and a unit redundant and a unit load applied at the redundant support. And a unit load applied at the redundant support. Okay. So I also want to go over some syntax, some terminology that I'll be using here. Let me say delta AO would be an example here. I'm going to use delta and delta, uppercase delta and lowercase delta. So for example, if I had a delta AO, a delta BO, and a delta AB, let me describe what these mean. Delta AO, delta BO, and delta AB. This would be the real deflection at some point A due to the loads on the primary beam. Due to real loads on the primary beam. And delta BO would be the real deflection at some point B. At some point B due to the real loads on the primary beam. Here. And then lowercase delta AB, this would be a deflection at, so again, all of these are going to use the terminology deflection at some point by a load at some point, or the O refers to just the general case, just to the general primary beam. Delta AB, lowercase delta AB, would be the deflection at A, but not due to the real loads on the structure. At point A, due to a unit virtual load at B. So my capital deltas will always refer, at least when I work through this method in this course, my capital deltas are going to refer to real deformations in the real structure. My lowercase deltas are going to refer to basically unit deflections, or deflection, I shouldn't say unit deflections, I should say deflections that come from unit loads applied at redundant support, typically at redundant supports. And I could also have, say, delta, I don't know, BB. This would be a deflection at point B, due to a unit virtual load at B. Unit virtual load at B. So again, we're going to have deflection at a point for the first subscript, and the second subscript is going to be showing what is causing that deflection. When we talk about just the general primary beam with the real loads, I'm just going to use an O or a naught to indicate that is just the general case. But if the deflection is being caused by a unit virtual load at a certain point, I'm going to put a subscript for that joint where that virtual load is applied. And this will become this kind of terminology. Now, when you're dealing with the case of the single or beams of indeterminacy degree 1, we only have a single redundant load. In those cases, it's the terminology, the subscripts you can probably get away with using, but especially when you start getting the systems that have higher degrees of indeterminacy, you really need some way of keeping track of all this, and your unit loads become important, or sorry, your subscripts here become important. So let me go over the general procedure for analysis, and then I'm going to go through a quick quantitative example, and then in the second portion of this, I'm going to go through a quantitative example. So let's go through the procedure, the general procedure. Let's set as a series of steps. And then we're going to, so again, I'm going to describe the steps, and then we're going to look at how we would apply those to a beam. So the first thing I'm going to do is determine the degree of determinacy, or find the degree of determinacy. I don't want to use the word determine all that much. The degree of indeterminacy. And typically, at least for beams, for a single rigid body like a beam, if you don't have like again, if you start having a frame or a beam with a moment release or something in the middle of it, in that case, it's not going to follow this simple relationship. For a single, again, rigid body like a single beam, the degree indeterminacy equals the number of reaction forces minus 3. All right, step 2 is going to be to select a reaction as the redundant, or I should probably say select reactions in parentheses as redundant force plural in parentheses. Again, because depending on the degree of indeterminacy, if you have a single degree of indeterminacy, you're only going to need one redundant. If you have 2, you're going to need 2, etc., etc. And you can just pick ones that are convenient. So in our previous example, or the previous beam I drew, where we had the cantilever, or sorry, the fixed support on one end and a roller on the other, I could remove a support on the right to turn it into a purely cantilevered beam. I could remove, say, the moment on the left to turn it into a simply supported beam. There are any number of ways to do this. And the direction that you pick for the unit load is arbitrary. is arbitrary. So 3, apply a unit load at the location of the redundant. Keep jumping forward. At the redundant. And then calculate at some point, and it can really be any point that is convenient. Calculate the deformation on the primary beam and the deformation on the secondary beam. On the secondary beam. Then finally, 5, apply compatibility equations and solve for desired quantities. Apply your compatibility equations and then solve for whatever you want. For the desired quantities. Let me show you what this looks like. So solve for desired quantities. So let me give you a basic example that would show what this would look like. And this is going to be a qualitative example. I'm not going to show numbers here, but I will go through the basic method here. And in part 2 of this lecture that I'll record later, I am going to go through and include some examples that actually have some numbers on them. Let me put those together first. So let's look at a basic example to illustrate this process. So let's go back to the beam we had previously. So let's say you have a beam that has a fixed support on one end and a roller support on the other. And then looking at the forces, let's say I have P here, a point load in the middle, then maybe an AX, an AY, and an MA. And then maybe there is a point load, or a reaction I should say, B at the end, BY. So currently this is indeterminate. I have 4 reactions, and I can really only solve for 3 using laws of statics. So therefore, this is indeterminate to the first degree. This is indeterminate to the first degree, so I'm going to need 1 redundant force. I need 1 redundant force. All right, so let's break this up into, again, using the principle of linear superposition, let us break this up into a primary beam and a redundant beam. And a redundant beam. So I'm going to show my primary beam, and again, this is going to be the beam with redundant reaction removed and under the real loadings. So I could find, so again, once I remove that load on the that reaction on the right, and I still have my load P here, well, suddenly this is a very easy problem to solve. You know how to do this. We've seen this many times before. This is fairly easy using equations from mechanics of materials or what we've looked at previously. There are any number of ways to solve something like this. So this thing would deform down like so, and there would be some, again, because this is point A and point B, I would have a delta BO. A delta BO here. Delta, capital delta, because we're talking about a real deflection. And this is the deflection. I'm going to annotate what these are. Delta BO is the deflection at B due to loads on primary beam. Due to real loads on primary beam. And again, because this is a statically determinate system, here, it would be very easy to find those. It would be very easy to find that delta BO. Okay, I'm going to try to squeeze this on this slide, so I'm going to erase this and rewrite my label here, secondary beam. Secondary beam. And so my secondary beam would be one where I have a unit load applied. So I'm going to apply a unit load at the location where I removed the support. So I'm going to apply a unit load, 1 pound, 1 kip, whatever is compatible with your unit system. And then there is going to be a certain deflection on this beam caused by this unit load. Like this. So I would have and this is going to be a lowercase delta because we're dealing with a virtual system. And this would be lowercase delta BB. This would be the deflection at B due to 1 kip unit load, or just, I should say, just due to unit load at B. Due to a unit load at B. And again, if you had some sort of a system with multiple redundants, then it'd be a bit more complex. We would need to have the multiple subscripts, etc., etc. But we could probably get away with it here if we wanted it. Okay. So this may look similar to virtual work, but now we're not actually really applying virtual work here. What we are saying though is we know that deformation in linear elastic systems is proportional to load. So I know that a 1 kip load will cause deformation delta BB on this thing at point B. So the deformation from the actual support BY is going to be, well, if this is, say, 10 kips, the actual deformation is going to be 10 times this. Again, because I'm assuming this is 1 kip here. If BY is actually 20 kips, and then the deformation should be 20 times larger. So let's say I find that this deformation is, 0.5 is 1 inch. Well, if BY is actually 20 times larger than the 1 kip load, well, that would mean the deformation is 20 times larger, so that would be 20 inches, although that would be a quite unreasonable deformation. So again, we can say, though, the real deformation caused by the reaction at B will not be BB, will not be delta BB. It will be basically BY over 1 kip times larger, or we can simply say that delta BB times BY. The actual real delta, the delta caused by the actual BY is delta BB, lowercase delta BB times your reaction there. And okay, so that may not seem very useful, but here's the thing. You can solve, because these are statically determinate, you can very easily solve for this delta BO. And in turn, you can also very easily solve for this delta BB. You know this. You have a 1 kip load, it's a statically determinate cantilever beam. It's trivial to find the deflection, that lowercase delta BB, from the 1 kip virtual load. And then we apply compatibility. Finally, you just apply compatibility. In other words, the total deformation at joint B must be 0. So we have the some deformation caused by force B upward. We have some deformation caused by the real loads downward. Those two, they must balance each other out. At the end of the day, they have to balance each other out. So I can say that the delta at B from the actual loads, the primary beam loads, plus the real delta at point B from maybe the unit load at B or the reaction at B is going to be equal to 0. Or, more useful, delta at B from the primary system loads, the real loads, plus delta BB, the deflection at B caused by a unit load at B, times By is equal to 0. This and this can be solved for directly. Can be solved simply. They can be solved for directly. And this By can be solved for algebraically. So this can be solved for algebraically. Again, once you have this and once you have this, that is a pre-algebra level equation. It's really not difficult to solve for By. Now, on systems where you have more redundance, sometimes you have to balance a couple linear equations, maybe 2 or 3 equations, maybe more, but really that's fairly trivial, so not too difficult. And so again, this is the real the deformation at B caused by the real loads on the primary beam with our redundant load removed, our redundant support removed. This is the deformation caused by at B caused by a unit load at B, and then we can set up this very simple equation equating them. So again, all it's saying is, ultimately all this is saying is, without that support, this load P would be capable of bending the beam down a certain distance, and then once we go back and apply the load that's actually there, the reaction force that's actually there, it's going to bend it back up a certain distance, and those two distances have to be equal. Again, linear superposition. And then you can just, and then once you have that, once you have By, the system is now statically determinate, can now be solved like any other statically determinate system. And so you can get whatever you want. Like any other statically determinate system. So what I mean by that is you're able to get, for example, you can get your, what can't you get? You can get your shear and bending moment diagrams, you can get your deflections, you can get your max moments, you can get whatever it is you want to get, whatever is required for your design. Once you have turned your indeterminate system into a determinate system, the rest is cake. Very easy. So, all right, that'll do it for my introduction to virtual work for beams. I hope you enjoyed watching this. Hope you learned a little bit. Let me know if you have any questions, and as always, thank you.